Question A. Here, if we try to substitute the value of 1 in the numerator and denominator, then we see that we get 0. Yeah, so for x going to 1, the numerator and denominator go to 0. So since we're dealing with polynomials of degree 3, we might factorize them. So first we try to factorize and take out the term x minus 1, and we do this by long division. So if we look at the polynomial, then we see that x minus 1 goes into x to the power 3 x squared times, and then the remaining polynomial is degree 2 minus 3x squared plus 5x minus 2. And x minus 1 fits like 3 times x minus 3 times x into this polynomial, remaining polynomial. And minus 3 times x minus 1 equals minus 3x squared plus 3x. So as a remaining term we get 2 times x minus 1, and x minus 1 fits 2 times into this term, and we get a remainder of 0, we should hold. Now the numerator, we try to take out the term x minus 1 out of this cubic term, x to the power 3 plus x squared minus 5x plus 3. First we see that x squared times x leads to x to the power 3 minus x squared, which leaves as a remainder 2x squared minus 5x plus 3. So we get as a remainder here minus 3 times x plus 3, and x minus 1 goes minus 3 times into this expression, which leaves a remainder 0. So now we may simplify the limit for x to 1 of the numerator divided by the denominator divided by the numerator. Yeah, by factorization, then we see that this equals the limit for x going to 1, x to 1 of x minus 1 times x squared minus 3x plus 2 divided by x minus 1 times x squared plus 2x minus 3. So now the terms x minus 1 cancels out in the numerator and denominator, and we are left with the limit x to 1, x squared minus 3x plus 2 divided by x squared plus 2x minus 3. Notice, however, that again numerator and denominator tend to 0 as x tends to 1. So look at these terms more closely, and we may again factorize and take out the term x minus 1 from numerator and denominator. So this equals x minus 1 times x minus 2, and in the numerator we get x minus 1 times x plus 3. So again x minus 1 cancels out, and now we have as a remaining term we may plug in or substitute the value of 1, and we obtain minus 1 over 4. B. Calculating the limit for x going to minus infinity. Well, this limit we can divide if we look more closely at the terms in numerator and denominator, and we look at the highest power that is presented there, then we see it's the square root of x squared in the denominator, which means a factor x, and this also holds true for the numerator. So we divide by the highest power in numerator and denominator. Yeah, the square root of 4x squared plus x plus 2 times the third root of x divided by x, and this again divided by the numerator x plus square root of minus x divided by x. This may be rewritten as x to minus infinity. Now we have to be careful. We want to write the x under the square root, and we must realize that for negative x, that x equals minus the square root of x squared. Yeah, so we may write the x squared inside the square root, if only we write a minus sign. And in the numerator we get 1 plus minus the square root of minus x divided by x squared. Doing this, we obtain the following: the limit of x to minus infinity of minus square root of 4 plus 1 over x plus 2 divided by x to the power 2/3, and this again divided by 1 minus the square root of minus 1 over x. So now we apply the rules for power functions. 1 over x goes to 0, 2 over x to the power 2/3 goes to 0, and minus 1 over x goes to 0. So we get as a limit minus the square root of 4 plus 0 divided by 1 minus 0 is minus 2. Question A, the precise definition of a limit of a sequence an. So the limit of n to infinity of an is L, which this means exactly that for all epsilon larger than 0 there must be an n epsilon, a natural number n epsilon, such that if we take a higher index than n epsilon, that for this index the absolute value of an minus L is smaller than epsilon. Well, here we have a specific sequence, which is minus 1 to the power 2 n plus 1, which is actually minus 1 times 2 to the power n divided by 3 to the power 2 n plus 2. And we will show that this sequence has a limit 0. Well, we start from scratch. Well, we try to construct an n epsilon for an arbitrary but fixed epsilon larger than 0. What do we know? Well, at least the difference of an minus 0, an absolute value, smaller than epsilon, is equivalent with the statement that, well, just plug in the formula we have for an. Minus 0 cancels out, should be smaller than epsilon, which is equivalent with the statement that, well, recall that minus 1 to the power 2n plus 1 is 1, minus 1 always, and absolute value will Now see that we have actually some common terms here. 2 to the power n and 3 to the power 2 to the power n, which makes 2 over 9 to the power n. And divided by 9. So if we multiply left and the right with 9, then we get 9 epsilon. Now we can get rid of the n as a power by taking logarithms to the left and the right, which leaves us with an equivalent sign here. So now we get n times the log of 2 over 9 should be smaller than the log of 9 epsilon. So now we divide on the left and the right by ln 2 over 9. And we see that the inequality sign flips because ln 2 over 9 is negative, a negative number, because 2 over 9 is smaller than 1. Yeah, so we still have equivalence, and now we get an expression like we want to have, since here on the right there's a number and here we see a condition on the index that we should take in order to have an at close distance to L. With close distance we mean epsilon distance. So if we round off this number, then we get n epsilon as a natural number, and then we see that if we even take a larger number than n epsilon, then the difference of an with the supposedly limit of the sequence 0 is no more than 2 to the power n divided by 3 to the power n plus 2. Yeah, which was already done in this stage. We just rewrote an absolute value of an, and then we rewrote this as 2 over 9 to the power n times 1/9. And we can just rewrite it as e to the power log 2 over 9n. Yeah, the e power and the log, they are inverse functions. So what is done here is just rewriting the 2 over 9 to the power n times 1/9. But then, of course, 2 over 9 to the power n was smaller than 9 epsilon. So we get that e to the power log 2 over 9 to the power n is smaller than e to the power ln 9 epsilon times 1/9. And here the number is just 9 epsilon times 1 over 9, 1 over 9, and then we get 9 epsilon times 1 over 9 is epsilon. So this is just exactly what we needed to show. Question B. Calculate the sum as corresponding to the sequence an for n is 2 to infinity. Well, we're first going to do the partial sums. So what are the partial sums? Well, Sn is a partial sum for n larger than at least 2, for k is 2n, and then summarizing over all relevant ak. So what we are doing is, well, first observe that minus 1 to the power 2k plus 1 is always minus 1, since 2k plus 1 is odd. So we take out the minus 1 over here, and we write further the sum of k is 2 to n over 2 over 9 to the power k times 1 9. Then we have a common term here, 1 over 9, and we can take it out again. So we're left with the following sum. Which equals, well, actually we see a term here, and we know that we recognize a geometric series here. So what we're going to do is let this sum start at 0. How we're going to prepare this? Well, first we write 2 over 9 to the power k. We take out 2 over 9 to the power 2. And now we see that the sum starts with k. If we plug in k is 2 here, then we start with 2 over 9 to the power 0. Well, this constant goes out to the front and we get this term here, and the sum of k is 0. Now we relabel within the sum, and we start with k is 0 and sum up to terms n minus 2, that's 2 over 9 to the power k. Now here we get a beautiful formula. For the partial sum. So we have a geometric series or a sequence an corresponding with the geometric series Sn, both with r is 2 over 9. So we get the sum S as a limit of the partial sums, and the partial sum is given by minus 4 over 729 times, well, here we plug in the beautiful formula we have for this kind of expression. The limit of n to infinity of 1 minus r to the power n minus 1 in this case, which means this is 2 over 9 to the power n minus 1, divided by 1 minus r, and r is 2 over 9. And now we see that this expression for n going to infinity cancels out, it goes to 0, so we're left with minus 4 over 729 times 1 over 1 minus 2 over 9 is, which is equal to minus 4 divided by 729 times 1 divided by 7 over 9, which makes minus 4 over 9 times 81 times 9 over 7 is equal to minus 4 divided by 7 times 81, or 567. The function g is differentiable if only the limit for h goes to 0 of gh minus g0 divided by h minus 0 exists. And this limit is of course equal in this case to gh minus g0. Well, 0 is 0 here, so g0 is 0 there, and h minus 0 equals h. So we're going to check whether this limit exists. Since we have an absolute value and this expression, we almost know the strategy we have to follow here. So we are interested in the existence of the limit of absolute value of h times e of h divided by h. And we distinguish the cases 1, which means that we let h go to 0 from the left, so it takes a negative value, so the absolute value of h equals minus h over here. So what we get is that the limit of h to 0 minus is minus e to the power h, as minus e to the power 0 is minus 1. The second case, we let h go down to 0, which means that h is positive. And if h is positive, we know the absolute value of h just equals h divided by h. And now the term h cancel here, we get simply e to the power h, which equals in limit e to the power 0 is 1. So now we see that the left limit and the right limit are not equal, so the limit will not exist. And if this limit does not exist, then neither g is differentiable at this point. Notice, however, that g is differentiable for other values of x, so that only at 0 this function is non-differentiable. Question A. You want to determine f prime. Well, here we see that f is a variable x to the power of some function which includes the variable in x, and we know that logarithmic differentiation might do something here. So we take the logarithm of fx, which equals the logarithm of x to the power sinus of x. We know that we can take the exponent down, so we are left with the sinus of x times the ln of x. Now we have an expression on the left, which is merely a function of x, and here we have a function of x. We can take derivatives on both sides, so we know that dx of the log of fx equals the derivative of the sinus of x times the ln of x, and we use the product rule here, so we get the first term, we take a derivative of the sinus of x, which is the cosinus of x times the log of x, plus the sinus of x times the derivative of ln x, which is 1 over x. On the other hand, we also know that the derivative of the log of fx is equal to 1 over fx times the derivative of the internal function, which is f prime, or the derivative of fx. So if we now combine these two facts, then we see that conclusion is that we know that f prime of x divided by fx equals the cosinus of x times the log of x plus sinus x times 1 over x. So if we multiply on the left and the right with the value fx, then we're done, because now we see that fx equals f prime x, or the derivative of f, equals the derivative of f times the cosinus x ln x plus sinus x times 1 over x, which equals x to the power sinus of x times the cosinus of x ln x plus the sinus of x times 1 over x. That's question A. Well, the answer to question B is quite short. If we recognize that actually x to the power sinus x over here on the top, that there's a sinus x inside, and for each x such that the sinus of x is 0, f takes on the value of 1. So if this happens more than once, then the function cannot be invertible, just for the reason that f is not injective. So you write it over here. For x larger than 0 with the sinus of x is 0, so when do we have this? Well, actually x should be of the following type, is pi plus a natural number times, let's say, k times pi. For k a natural number, well, maybe 0, then we know that the sinus of x is 0, so that fx for these x's equals x to the power sinus of x equals to the power x to the power 0 equals 1. So for 1 in the range of f, there are many originals. Put otherwise, f is not an injection, hence not vertible. Well, we could have taken other values, of course, but this is the easiest one. Well, in A we are supposed to calculate the derivative of y as a function of x. So assume that y is y of x. Then using implicit differentiation we take the derivative here, which is not more than the left of the equation, and we take a derivative of the right hand side of the equation, which is d dx of y. And now we calculate on the left and the right the derivative as if we knew the derivative of y. So here we get the derivative of x plus 1 to the power 3, and this is a more complex term, so we have to be careful there. So here we first use the product rule, y prime, which is the derivative of y, and now we get y times the derivative of the sinus of x over y, which is the cosinus of x over y, and using the quotient rule for x over y. And on the right hand side we get simply y prime. So now we gather all terms y prime. One is here, and one is here, y times the cosinus of x over y times minus x divided by y squared. So then we get this amount of y prime. There should be x written here. Check it very carefully. And then we y prime on the right hand side. If you move it to the left, you get minus 1. So minus 1. And we put anything else we put to the right hand side of the equation, equality. So we get 3 times x plus 1 squared will go to minus 3x plus 1 squared, and we get another constant term, or a constant depending on y and x only, and not on y prime, which is y times, well, we collect these terms, and we get this expression here. Y squared divided by y squared times the cosinus of x over y. So here we get y prime times the sinus of x over y minus 1 over y, because y cancels out, or times x times the cosinus of x over y minus 1 equals minus 3x plus 1 squared minus the cosinus of x over y. Well, this is just equivalent with saying that y prime equals, well, the right hand side, which is just repeating what we've written before, divided by the sinus of x over y minus x over y cosinus x over y minus 1. So if you like to think of what this means, well, this is actually the derivative of y over x. Y moving with x as a solution of equation 1. Well, what can we do with it? Well, for instance, we could take derivatives. If you know some solution, like we have here, x0, y0 is 0, 1 in C, then we might see the marginal change of y related to a marginal change in x from x0. It's just plugging in the x here, x is 0 and the y is 1. So we get minus 3 times 0 plus 1 to the power 3 minus cosinus 0 divided by sinus 0 minus 0 over 1 times cosinus 0 minus 1, which equals, well, minus 4 divided by minus 1, which equals 4. Yeah, so the marginal change of y related to a marginal change of x0 is 4. So if we take a small step in x, then what we are likely to see is that our solution of approximately the y component on the curve will change with 4 times the delta x, or the change in x. Show that for each choice of y unequal to 0, there exists at least one x such that xy is a solution of the equation 1. Well, suppose we have a given y unequal to 0. Now we introduce a help function. Why we do this will be clear in a minute. Fx is equal to x plus 1 to the power 3 plus y times the sinus of x over y. Well, we take y as a constant, so here there's a function, truly a function of only x, and f is continuous. Yes, a sinus function plus a polynomial, a power function. Well, first observe that if we look at a component of y of f, y times the sinus of x over y, the sinus of x over y is smaller than 1 in absolute value. So we know that this is a bounded component in this way. Yeah, so we have a bounded component in f for a given y. But this f also has an unbounded component, which is x plus 1 to the power 3. Or in particular, we know that the limit for x going to infinity of x plus 1 to the power 3 is infinite. And the limit to x to minus infinity of x plus 1 to the power 3 is minus infinity. So we see that f takes on arbitrary large values as well as arbitrary low values. So especially one observation is that there should be an x star with fx star larger than y. And there also is an x double prime or a double star with fx double star is smaller than y. Going to minus infinity, we get arbitrarily low values of x. And here it says that we get arbitrarily large values of x. So we find a larger value of y and a lower value of y. So the intermediate value says that actually a continuous f, for moving from x star to x double star, we should have equality for some x with y. So there should be a solution to the equation fx is y. And a solution to this equation is actually what we needed, because here in the exercise we see on the left hand side of the equation we get f, and on the right hand side we get y. So we have seen that for some fixed value of y we get an x such that f of x, which stands here, equals y. While determining the equation of the tangent line to the solution curve for 1 in a point 0, 1, well, in A we've seen that actually if you calculate the derivative of y in 0 for the values x0, y0, 0, 1, that we get y prime 0 equals 4. So using the standard way to put up an equation for the tangent line or a line which goes through coordinates 0, 1 and has RC of 4, we get L is y minus y0 equals to y prime 0 is 4 times x minus x0. So rewriting this using the values, we get y minus 1 equals 4 times x minus x0, but x0 is 0, so we might as well express L in terms of x. X is 1 over 4 times y minus 1. So if we take a slightly more bigger value of y, like 9 over 8, then delta y equals 9 over 8 minus 1. Then if we move along this line, then we suspect that the disturbance or the change in x value is actually 1 over 4 times 1 over 8. Yeah, 1 over 4 times delta y is 1 over 32. So actually if we try to find an x value such that x1 9 over 8 specify a nearby solution of the equation, our best guess will be to move along L, at least as a linear approximation to this value. So we get x1 is 1 over 32. since changes are measured with respect to the x0 coordinate, and x0 coordinate is 0.